Lab 5 Choose Your Own Adventure by Swayam Sanket Kumar Trivedi. Introduction. Purpose. The purpose of this lab is to predict the motion of a stretched slinky dropped from static equilibrium and the effects of the surroundings on it. We shall carry out this lab by using tracker to track its observed position and a closed grip model to predict the ideal motion of the slinky. The final objective is to determine if the bottom of the slinky remains stationary. The fundamental principles used are Newton's second law, gravitational force, drag force. Preview of the main results. Even though there was some fluctuation, the bottom of the slinky remained stationary. The main physics ideas used in this lab are Newton's second law, which states that a system's change in momentum is directly proportional to the net force applied. The F net in this case is the force of the spring and gravity, hence we use this equation. Another physics idea is the force of gravity or gravitational force, which pulls objects with mass towards each other. This can be found by the formula mj hat, which in our case, as it is on Earth, is mass times gravity, which is 9.81 meter per second squared, times the change in displacement. Drag force is the resistive force that is caused by motion of a body through a fluid like air. It can be found by the formula minus b modulus v to the power 2 times v hat, where b is the proportionality constant, v is the speed of the object, and v hat is the direction of velocity. Other useful formulas include the velocity update formula, which is final velocity is equal to initial velocity plus the change in acceleration times the change in time, and the second one is the position update formula, which is the final position is equal to the initial position plus the average velocity of the object times the change in time. Observed motion. The system in this case is the slinky, the surroundings is the Earth, and the initial conditions is where the mass of the slinky is 0.218 kg. The initial position is negative 1.632 times 10 to the power negative 3 in the x-axis, and in the y-axis is 2.725 times 10 to the power 4 in the y-axis. The initial velocity is 0 meters per second. I then used GlowScript in order to create a computational model in which the initial conditions were kept as the spring mass as 0.218 kg, the spring velocity is 0, and the spring position as the same as the one in the tracker. T was at 0 and delta was at 0.01. The gravity was kept as 9.8 meters per second squared, while J hat was the vector 010, while B, which was the drag proportionality constant, was kept at 75. I then did it for the first loop, in where the time when bottom of slinky is constant was 5.5333, while I maintained the rate of 100. The gravitational force acting on it was minus the mass of the spring times gravity times J hat, while the slinky tension force was equals to the gravitational force. The velocity update was ball velocity, the formula that I provided, and I also changed the position update formula. I then took into account where the slinky is now moving as a whole, and the time it takes for it to reach the ground, which was less than 8.133. The gravitational force, I also introduced the gravitational force and drag force, in which I placed in the formula of drag force. I also introduced the ball velocity and the ball position at that time. I then compared the data between the tracker and the computational model in order to get resulting graphs, through which I was able to determine that they follow a quite similar system. However, the observed data has a few fluctuations compared to the predicted, which is just a straight line going horizontally before dropping down, and this is because of external factors that could affect it. Some of these factors that could have affected it were parallax error or judgment of free-fall start endpoints, while for the computational model, it could be due to precision errors in measurements. Some assumptions that are taken is that the object falls in a straight line and it's a point-like object. What if? What would happen if a large weight was introduced at the bottom of the spring? The answer to this question depends solely on the slinky's properties. If the slinky had sufficient length or a high enough spring constant to create a tension force equal to the gravitational force, the bottom of the slinky will remain stationary until the top of the slinky reaches it. However, this scenario is idealized and applies primarily to computational models. In a real-life world system, fluctuations may occur. What does it mean? What does it mean when the slinky remains stationary? The force in the y direction cancel out, although gravity pulls downwards on the slinky. It remains nearly stationary because the slinky, acting as a large spring, generates an upward tension force equal to magnitude and opposite in direction to the gravitational force. Conclusion. Newton's second law was used in this experiment. The position of the bottom of the slinky was analyzed and now gravity and drag affected. Computational model was created and compared to the observed data. In the real world, other forces are acting on the slinky system, causing vibrations in the resulting graph. Thank you.